Hi folks, and welcome back to Math with Captain Rod. The purpose of this video is to demonstrate how to numerically integrate, basically. So as a numerical example, we're going to look at the function y equals x squared plus 3, and we're going to try to calculate the area bound between that function x equals 1, x equals 4, and the y-axis. So we're going to look for this area right here. Now, in integral language, this would look like this. We would draw a differential rectangle. The area of that rectangle would be f of x dx, and this would be integrated from 1 to 4. Now, I realize this is a very simple integral to work. I like to use simple examples when I'm introducing new concepts because I don't want people to get lost in the complexity of the function. We're going to talk about how to use Microsoft Excel to set up a very similar calculation to calculate the area under that curve. Now, when you set up an integral, the differential element here you can be kind of lax about, basically. How it interacts with this curve is really not important. So if you've seen my previous videos on this, you have upper bound, or you have like left end estimates, right end estimates, and midpoints. And when you're using an infinite number of n, which is what this thing does, all setups will converge to the same value. Therefore, you don't really have to pay too much attention to this. When you're setting these up for numerical work, you do. So what I'm going to do is I'm going to set this up using 10 rectangles. So I'm going to say n equals 10. My lower bound is 1, my upper bound is 4, and I'm getting those right off the curve. Right away, I can calculate a delta x. All right, delta x is b minus a over n. In this example, that'd be 4 minus 1 over 3, which is 0.3. Now, when you're working numerically, you do have to pay particular attention to how we set these up, and I like to use the midpoint rule. See, if I set my rectangles up like this, etc., I'm going to be including areas here that are not actually bound. You're going to get an answer that's a little bit too big. If we set our rectangles up like this, etc., we're missing areas here. We're going to get an answer that's a little bit too small. So we're going to use what I call the Goldilocks method, or the midpoint formula. If we set our rectangles up like this, so that the function goes through the center of the rectangle, that's going to give us, of the three choices, the best estimate for the area under the curve. Because we're overestimating on the left-hand side here, but we're underestimating on the right-hand side, and those two things effectively cancel each other out. Now, I've kind of exaggerated the size of these rectangles. This is 3, the delta x is 0.3. I did that because I need a really good picture of that first rectangle. Notice that the first rectangle area is length times width. The width we know to be 0.3. Here's a very important fact. The length is the function value at this x coordinate right here, which would be 1 plus half of a delta x for any delta x. The second rectangle, the area is going to be length times width. The width is the delta x. The length is the function value, but it's very important to recognize where. I'm going to put red dashes here. So here's our first one. Here's our second one. So you'll notice if I keep going and I draw more rectangles, there's very discrete x values that we need. The first one is 1 plus half of a delta x. The second x value is 1 plus half a delta x plus another delta x. That's 1 plus 3 halves delta x. The next rectangle, we're going to have to move over another delta x, and the next rectangle, another delta x, and so forth. So what I'm going to do now is I'm going to set up a little formula here to calculate that. Now, you'll also notice that, okay, we have our first rectangle, our second rectangle, there's going to be a third rectangle, all the way to 10 rectangles. So in effect, I've introduced another variable here. This is what's called a dummy variable. It's just a variable that keeps track of the different rectangles. I'm going to call that I. In this example, I is going to be 1, 2, 3, down to 10. What I'm going to do is I'm going to calculate then x, what I call x sub I. the x value at the center of the ith rectangle. So x1 would be like right here. x2 is right here, center of the second rectangle. x3 is center of the third rectangle, and so forth. Now, my game plan down the road is to use Microsoft Excel to do this. And what we're going to need is we're going to need a formula here that will calculate all of these rectangles for us. Now, here's something to point out. Look at the product 1 times delta x. I'm sorry, I got to back up. 1 plus 1 times delta x. If you look at what that does, 1 moves us to here, plus 1 times delta x would put us at the right-hand side of the first rectangle. 1 plus 2 times delta x, right, puts us, 1 plus delta x plus another delta x. That puts us at the right-hand side of the second rectangle. 1 plus 3 delta x puts us at the right-hand side of the third rectangle, and so forth. In general, 1 plus I times delta x would put us at the right-hand side of the ith rectangle. So, for example, if I was 7, 1 plus 7 delta x would put us right-hand side of the 7th rectangle. Now, again, we don't want to be at the right-hand side. We want to be at the middle, the center. So every one of these has to be shifted left by half of a delta x. I can do that in my formula by going minus 0.5 times delta x. What I have here now is a formula that will put me at the center of any rectangle I choose. I can pick any value for I, put that number in, and I will have the x value at the center of that rectangle. And what I'm going to do now is I'm going to have Excel calculate what I'm going to call A sub I, area of the ith rectangle. Now, the length of the rectangle is the function value at the appropriate spot. And then the width is delta x. So the area of the ith rectangle, I could write f of x sub I times delta x. Now, since the f of x is x squared plus 3, I could actually write that x sub I squared plus 3 in place of this times delta x. So the idea here now is for every I value, go through and calculate an x sub I, go through and calculate an A sub I, an area for that rectangle, and add them all up. With a calculator, that would be quite a bit of work. But Microsoft Excel is an awesome program for doing work like this. It does this kind of rote work very easily. So what I'm going to do now here, I'm going to kind of pause my video. I'm going to pull up Microsoft Excel and start now doing the video work, or start going through the Excel work on the video. So bear with me. Okay, folks, I'm back here. This is going to be a little hard to follow here because I need two screens going at once, but I'll do my best. So again, what I'm trying to do here is I'm trying to find the area under this curve. What I'm going to do is try to set myself up a table that's going to calculate this stuff that I've talked about a little bit earlier in the video. So what I usually do is I start by putting all the what I would call data that we're going to need, things like this. We have a lower bound that we're going to need and an upper bound. So I'm going to come here and type A to represent the lower bound. In this case, the lower bound is 1. We have an upper bound B. In this example, that's 4. We chose a number n for the number of rectangles. In this example, that's 10. And the first thing I'm going to do here is I'm going to have Excel calculate our delta x. I'm going to label it del x. That's just a label. I'm going to move over, hit equals. Now delta x is B minus A over n. And you'll notice that rather than typing those values, I'm clicking on Excel cells. Now the cool thing is, by setting it up like this, if I go back and I want to change this, instead of 1 to 4, I want to go 1 to 6, I just go back there, hit 6, boom. You'll notice that when I change the 4 to a 6, Excel automatically updated my delta x, which is a really nice feature. So I'm going to go back, change that back to 4. All right, now looking over here, now I want these values here. I want Excel to give me the i's. So I'm just going to list I, and then 1, 2, 3. Now you don't have to type them all. if you click and highlight these three, once you show Excel a pattern, it's really good about filling the rest out for you. So I'm going to have 10 I values. Okay. Now I'm going to have it calculate what I call the x sub i's, the x coordinate of the center of the ith rectangle. And I'm going to plug this formula in here. Now when you put a formula in Excel, the first thing you have to do is hit equals. And it's 1. Now instead of typing the 1, what I'm going to do is that 1 is the lower bound. So what I'm going to do is I'm going to just click right here. 1 plus I times delta x. Right? And then again, this part, minus 0.5 times delta x. So we're going to need a minus 0.5 times delta x. Okay. Now, Excel, once you give it a formula, is really good about calculating a bunch of them for you. So when you want to do a calculation, what you do is you grab and you drag down. This, in theory, should calculate all of them. If it's done correctly, this last one right there should be just short of 4. And you'll notice there's a bunch of problems. Now, whether you believe it or not, I did this deliberately to demonstrate this. So Excel is also very good about telling you what it did. So I see, all these different problems here. I'm just going to click on one of the problems and try to figure out why this happened. I don't know. I'm going to click right here. So what did it do? It took this 10, added it to 3 times, or added it to, well, the important thing here is it's using cells it shouldn't have. Right, if I click right here maybe, or right here, you notice those blue and those purples are scrolling down. Or if I go backwards, they're scrolling up. You'll notice that the red one is scrolling, and so are these. We want the red one to scroll, but anything we reference up here, we do not want to scroll. Those need to be stayed locked down. So what we do is we go back to the original formula. I'm going to click on it. Anything that's blue or purple needs to stay put. That's going to be this A9, or I'm sorry, that's going to be this guy and this guy. So actually this guy too. I'm going to come right here behind this B1. That's one that we want to stay put. It's blue. And if you hit F4, what you'll find is it inserts those dollar symbols. I call this double dollaring. What that does is it tells Excel, do not let that cell move. Every time you reference it, you go to that exact spot. Anything that's blue or purple needs to be double dollared. So I'm going to come over here and double dollar that guy, F4, double dollar this guy, F4. This command is good for any PC I've ever seen. If you're an Apple user, you're on your own. It will have an equivalent command, I just don't know what it is. Grab, drag. If I have this right, the last one should be 3.85. Boom. And I got that by taking 4 minus half of 0.3, the delta x. All right. Now, we need Excel to calculate the areas. Now, we can do this a couple different ways. I'll go ahead and I guess do just like I set up. One thing is I could have it calculate the function values, scroll those down. Then I could have it calculate the areas. But because I did this, I'm going to be consistent with exactly how I set it up. So A sub I equals, all right, so now we need the function value times delta x, and the function is x sub I squared plus 3. So equals, I'm going to put this in parentheses because I know that we're going to be multiplying by delta x. So there's my x sub I squared plus 3, close parenthesis. There's my function, my f of x sub I. Now I'm going to multiply that by delta x, which is up here. Whoops. Did something that didn't like there. Okay, so we got my x sub I squared plus 3 multiplied by, and I'm going to come here and click on delta x. Now, anything referenced up there, we don't want it to scroll, so I'm going to go ahead and hit F4. That double dollars that delta x. So the area of that first rectangle should be about 1.29. Cool thing is in Excel, grab, drag, it will do all of them. And now what we want to do is just add these all up. So I'm just going to come over here and put something like a total. Over to the right, I'm going to hit equals. Excel has a whole truckload of different types of mathematical commands. One of them is summation, sum, and all you got to do is highlight them. That sum looks like about 29.8. Now, I'm going to go ahead and take a moment here and check this by direct integration. I've got to flip my computer around. Again, looking back here, the area here was integral x squared dx from 1 to 4. That's going to give us x to the third over 3 plus 3x from 1 to 4, which is going to be 4 to the third over 3 plus 3 times 4 minus, and I'm running out of room, so I'm just going to put 1/3 plus 3. Well, 1 cubed over 3 plus 3. And I'm going to take a moment here and ask one of my helpers here to calculate a value for me, please. 4 to the third over 3 plus 3 times, 4 to the third plus 3 times 4 minus 1 to the third plus 3 times 1. If somebody would give me a numerical value there, I'm guessing it's going to probably be 30. Or should be pretty close unless there's a mistake. And if there is a mistake, we'll go back and figure out where it's at. I think I'll pause this here while I wait for my helpers. 30? 30, spot on. Okay, so this came out to be 30 identically. Now, one thing I want to point out, we got 29.978. I want to talk about the error there in that calculation. So our percent error is going to be the expected value minus the calculated value, 29.9. I'm going to go ahead and write 78. I'll round to that guy right there. Divide by our expected value times 100. Would somebody please calculate this? 30 minus, whoops, I got that decimal in the wrong spot. 29.9. I'll just round it right there. We'll just round it right there. Divide that by 30 times 100. Again, I'll pause this while what'd you get? And that's already multiplied by 100? 0.075%. Oh, and we got somebody got a 0.066. Let's get a third opinion. Got a couple of votes at the 0.066, so I'm going to go with that. Now, you know, whether it's 0.66 or 0.75, not important. The thing I want to point out is this has already had the 100 multiplied. That's less than 1/10 of 1%. That's really, really, really good. And we did this with only 10 points. One way we could have made the calculation a little better is maybe use 20 points, because as the number of rectangles gets more and more and more, your error gets less and less and less. Now, one thing I want to point out, that's not true indefinitely, because there's another type of error that starts becoming involved. Every time you do more calculations, there's round-off error. And as your number of rectangles gets larger and larger and larger, your round-off error gets larger and larger and larger. So going from 10 to 20 certainly is going to give us better results. But in the future, you got to keep that in mind, that there are other types of error besides the geometric error affected by n. There's also round-off error. All right, good rule of thumb, the larger value of n will give you better results. So anyway, I just wanted to go through an example of how to do a basically work an integral numerically in Excel. Notice how easy it was with only 10, using how easy and accurate it is using only 10 points. Now I realize that this function value is, like a little kitty function here, but the method is exactly the same no matter how complex the function. And as long as Excel can compute function values, it doesn't really matter how ugly this thing is. So Excel is a wonderful way for calculating, for doing integrals. This method works great, provided that you can find the antiderivative for this function. Excel doesn't have that hindrance. All it needs to do is calculate function values for these things. As long as it can do that, it can calculate an integral. Now there's some more details that you learn later in calculus about integration across asymptotes and things like that, and I'm going to save that for another video. But anyway, I hope this video helps demonstrate how to use Excel to numerically calculate an area under the curve. Have a great day.